Assalamu alaikum dear students. In today's video, we'll be diving into the world of linear programming again and exploring another technique which is called M method. This is also called big M method, and this is also known as penalty method. So we have already learned the Simplex method, which is a powerful tool for solving linear optimization problems, but it assumes that we already have a basic feasible solution to start with, which is called initial basic feasible solution. This means that all our initial constraints must be satisfied and we need a starting point that is already inside the feasible region. So such a solution is found by using the slack variables as our basic variables. Basic means non-zero variables. Because we dealt with all the constraints of less equal type. But what if this is not the case? That is, if an LP has any greater equal or equation type constraints, then an initial basic feasible solution may not be readily apparent. So this is where the M method comes into play by introducing artificial variables and assigning a very large penalty M to them. So this is how we can force Simplex algorithm to find a feasible starting point even when it does not exist naturally. So this can be done by introducing artificial variables which play the role of slack variables and allow Simplex method to begin the process. And as we go through the iterations, we work towards eliminating these variables while driving the solution towards optimality. So in this video, I'll walk you through the steps of M method, showing you how it overcomes the limitation of Simplex method and solve the problem when the constraints are not of less equal type. Okay, so let's learn the process with the help of this example. In this example, we have to minimize the objective function z is equal to 4x1 plus x2 subject to the constraints 3x1 plus x2 is equal to 3, 4x1 plus 3x2 is more than equal to 6, x1 plus 2x2 is less or equal to 4. So our first step would be to transform this system into an equation form that is called standard form. So this is how we can transform these constraints into equation form. So first constraint is an equation, so we'll write it as it is. Second constraint is greater equal inequality, so we have to subtract a surplus variable from left hand side to make it an equation, and that surplus variable in this case is x3. And in last constraint we have to add a slack variable which is x4 in this case, and this is how equation look like. So this is the standard form of this system. So now if we start with the origin, that is all decision variables equal to 0, x1 0, x2 0, as we did in Simplex method. So in this case you can see that when x1 is 0, x2 is 0, first equation becomes 0 is equal to 3, which is not possible, false. And in second constraint, if we plug in these values, we found out that x3 is equal to negative 6, and this is no more a feasible solution because all the variables are non-negative and they must be non-negative initially. So we have to add artificial variables as a slack variable. So the system looks like this. Here R1 is a slack variable, artificial slack variable, R2 is also an artificial slack variable. In this equation we added R1, and in this equation we added R2. So whenever we have equation or greater equal type of inequality, we have to transform the system into equation first, and then we have to add artificial slack variables whenever needed. Now in order to penalize these artificial variables, we have to modify our objective function too, so that these artificial variables do not affect our actual problem and actual optimal solution. So in order to penalize, if we have a maximization problem, we have to subtract m times sum of artificial variables from actual function. But in case of minimization problem, we have to add m times sum of artificial variables into the original objective function. So since this is minimization problem, so our modified objective function is 4x1 plus x2, that is the original part of the objective function, and this is penalized part of the objective function, m times r1 plus m times r2. Now we'll start with initial tableau of the simplex method, and for this we need an equation from this objective function as well, and let's write corresponding equation. Z minus 4x1 minus x2 minus mr1 minus mr2 is equal to 0. So this is the initial tableau of simplex method. So left column is dedicated to basic variables, that is non-zero variables. So these are the variables involved in the system, and this column, extreme right column, is dedicated to solution. So if we fill all these spaces, so we have this. So this is R1 row, which represents all the coefficients and solution in the first equation. So this actually tells us that initial value of R1 is 3. Similarly, this is second row, and slack variable for this second row is R2, and all the coefficients are written in this row along with the solution, that is initially R2 is 6, R1 is 3, and x4 is 4. And similarly, we have written Z row as well. But before proceeding further, let's check whether this initial solution is consistent with this objective function. That is, we have to check whether this solution satisfies this objective function or not. So we have Z minus 4x1 minus x2 minus mr1 minus mr2 is equal to 0. But we have r1 is equal to 3, r2 is equal to 6. When we plug in all these values, and x1 is 0, x2 is 0, so this becomes Z minus 0 minus 0 minus r1 is 3, so 3m, minus r2 is 6, so 6m is equal to 0. So this gives us Z is equal to 9m. But from this row, 0, we can see that Z is equal to 0. So this row is not consistent with rest of the rows. So we have to modify this objective function, and for this we have to substitute these artificial variables out from the objective function. So in order to do so, we have to find the values of R1 and R2 from their corresponding equations and substitute into this objective function, so that R1 and R2 are substituted out of objective function. So from equation 1, we have R1 is equal to 3 minus 3x1 minus x2, and R2 from equation 2 is 6 minus 4x1 minus 3x2 plus x3. So substitute these values into the Z expression. So 4x1 plus x2 plus m times r1 3 minus 3x1 minus x2 plus m times 6 minus 4x1 minus 3x2 plus x3. So let's simplify this. So Z is equal to coefficient of x1 is 4 minus 3m minus 6, that is, okay, this is 4, minus 4m, so minus 7, and plus x2, coefficient of x2 would be 1 minus m and minus 3m, so minus 4m. And we have x3 here, so plus mx3. And what else? We have 3m here, we have 6m, so this is plus 9m. So in order to make computations easy, if we assign some large value to m is very large number. So if we assign a large value to m, large in comparison of the coefficients of objective function or coefficients of constraints. So in this case, 100 will be large enough as compared to all these coefficients. So we can assign m is equal to 100. So this becomes negative 696x1 minus 399x2 plus 100x3 and plus 900. So our new z equation becomes z plus 696x1 plus 399x2 minus 100x3 is equal to 900. So this is, now system is consistent. Since R1 is 3, R2 is 6, so our z should be 6m, that is 6 times, our z should be 6 plus 3, that is 9m, that is 9 times 100, which is 900. So let's replace this 0 by these coefficients. So this is our new 0. 696 is the coefficient of x1, 399 is the coefficient of x2, negative 100 is coefficient of x3, and coefficients of 0, r1 and r2 are, and x4 are 0, and initial solution is 900, and initial basic feasible variables are r1, r2, x4, and their solution is 3, 6, 4 respectively. So now we have to do the iterative process of simplex method to find out optimal solution. So since this is minimization problem, so we have to find out the variable in z row with most positive coefficient, and that would be the candidate of entering variable as a basic variable. So in this case, x1 is the coefficient of x1 is most positive. So x1 is going to enter as basic variable, and in order to find which variable is going to leave as basic variable, so we have to find out the ratios of this solution and the pivot column. So these are the ratios, and least positive here is this one, that is our 1 is going to leave, and this is going to be non-basic variable where x1 is our next basic variable. So this is our pivot row and this is our pivot column. So let's apply Gauss-Jordan row operation. So we have to have pivot element as 1. So just divide pivot row by 3. So we have this new pivot row. x1 has been entered as basic variable and r1 has left. So rest of the variables are r2 and x4, and our target is to convert all these entries in the pivot column as 0. So we have to perform row operation in order to make this element 0. So that would be row z minus 696 times this row, this pivot row, new pivot row, that is row x1. So this allows us to modify 0 as shown. Similarly, we can modify rest of the rows. So in case of R2, we have to do that row R2 minus, here we have 4 and we have to make it 0. row R2 minus row X1, this pivot row, and we have to multiply this by 4 so that we can get 0 here. So this is the new R2 row, and similarly we have this X4, new X4 row. So again, since we can see some positive coefficients in the 0, so solution is not optimal, and we have to perform another iteration, and we have to decide an entering variable. So in this case, the only positive coefficient is x2. So this is going to be next entering variable as basic, and one of the variables have to leave. For this, we have to find ratios. Similar procedure you have already learned in simplex method. So the ratios are 1 divided by 1 over 3, that is 3. And in this case, 2 divided by 5 over 3 means 3 over 5, that is 6 over 5. And in this case, 3 times 3 over 5, that is 9 over 5. So this is the lesser one, so least positive. So that is why R2 is going to leave. So both the artificial variables have left the basic position and they have become non-basic. So again, repeating this procedure couple of times, we have the optimal solution, and this is the last final tableau of the simplex method, and we can see we don't have any positive coefficient in 0, so we have achieved optimal solution, which is z is equal to 17 over 5, x1 is equal to 2 over 5, and x2 is equal to 9 over 5, and x3 is equal to 1. Rest of the variables are 0, that is x4 is equal to 0, and r1, r2, both artificial variables are also equal to 0. So this is the whole process. Now there is a note, and you need to remember this. If the final simplex iteration includes at least one artificial variable with a positive value, this will indicate that the linear program does not have a feasible solution. This is very important to note. So if we have artificial variable as basic variable and their value is positive, then the problem does not have a feasible solution. That is, the constraints cannot be satisfied simultaneously. So that's all for today.